exploded as supernovae. Those explosions created the iron, ejected it into the cosmos, and then it got incorporated into planetary systems like ours. But ultimately, the atoms of iron were created by exploding stars.
Supernovas are the industrial zones of our star city. Cosmic foundries that forge new elements. In catastrophic explosions, heavy elements are spewed out into our galaxy, enriching it over billions of years.
So if some stars were not to explode in the industrial zones of galaxies like our Milky Way, then we wouldn't have these industrial zones here on Earth. It all is linked. We're all linked to the cosmos.
Our lives today are only possible because of events that happened thousands of millions of years ago in the hearts of supernovas.
It's fascinating to realize that the heavy elements in our bodies, the carbon in our cells, the calcium in our bones, the oxygen that we breathe, the iron in our red blood cells, all of those heavy elements were synthesized, created through nuclear reactions in stars, and ejected into the cosmos by supernovae.
But only a handful of stars are massive enough to die as supernovas. Most stars, like our Sun, suffer a more gentle death.
Most stars don't die in a cataclysmic explosion. Our own Sun, for example, a typical star, will die with a whimper, not a bang.
Death comes when the gravity pulling in finally succumbs to the nuclear energy pushing out. When this happens, any star, even our Sun, will die.
In about 4 or 5 billion years, it'll grow into a much bigger star, a star called a red giant. And the outer atmosphere of gases will be held so loosely by the Sun at that time that the gases will be blown away gently in what I call a cosmic burp.
These cosmic burps leave behind dying stars that litter the spiral arms as they slowly shed layers of elements.
Some layers are oxygen, and some layers are silicon, and some layers are sulfur. And those are the different colors we see in the Hubble Space Telescope images.
Not far from our Sun is a place where a star is dying. The Helix Nebula. It sheds light on how most stars end their lives. Our Sun is destined to follow a similar path when it dies, 5 billion years from now. But in other neighborhoods in the galaxy, stars suffer a fate worse than death. At the center of the galaxy lies a place where stars disappear altogether. We're taking the Earth from the safety of home to go downtown to the heart of the Milky Way. It's a dynamic, exciting district, but it's also a risky place to hang out. Andrea Ghez has spent over 15 years exploring this neighborhood.
If we were to take a trip from the spiral arms out where we are by the Sun down to the center of the galaxy, it would be an interesting trip. It would be very much like moving from the suburbs into the heart of a very busy metropolitan area.
As we head downtown, the number of stars increases.
So the density of stars is tremendous at the center of the galaxy. It's about 1 billion times higher than out here by the sun.
Here at the center of the galaxy, there are so many stars in the sky that the Earth is bathed in perpetual light. It's a stunning but dangerous sight to behold. The stars aren't just close together. They're moving at super speed.
Going to the heart of the galaxy might not be dissimilar to going to an amusement park. The rides are somewhat similar to how the stars orbit the center of the galaxy. 10 million miles per hour compared to, say, our sun is about a factor of 50 times faster. So something has to be going on at the center of our galaxy to make that happen.
But figuring out what is no small task. The heart of our galaxy lies 26,000 light years away. It's difficult to observe through the vast amounts of stars, gas, and dust. And there's another problem even closer to home: the Earth's atmosphere.
The atmosphere is great for us. It allows us to survive here on Earth, but is an absolute headache for astronomers. It's very much like the problem of looking at a pebble at the bottom of a stream. The water in the stream is moving by, and it's turbulent, and it makes it very difficult to get a clear vision. In the same way, looking through the Earth's atmosphere prevents us from getting clear pictures of the stars at the center of the galaxy.
So astronomers like Guess turn to a technique called adaptive optics to get a better view. By measuring how a laser beam is distorted in moving air, it's possible to compensate for the atmosphere's blurring effect.
So let me show you an example of how powerful adaptive optics is. The stars that we want to see are the ones that are at the very center. We think the heart of the galaxy is right within the center of this box, which is panned out here. Without adaptive optics, this region looks completely blurry. You don't see the individual stars. With adaptive optics, you see the individual stars.
For 15 years, Des has taken infrared images of the stars at the heart of the galaxy to produce an extraordinary time-lapse movie.
So if we zoom into the very heart of the galaxy, we can actually see the data that we've taken over the last 15 years, and you can see the stars, and you can see the tremendous motion that they've gone through. In particular, SO2, which is my favorite star. Every astronomer has a favorite one. So you can see SO2 goes around, and in particular, you can see as it gets to the center of the frame, it moves much more quickly. So something's interesting as it goes through that region. So putting everything together, all the measurements that we've made, we've been able to make an animation that shows how the stars have moved over the course of 15 years. Each star goes whipping around the center of the galaxy. In particular, the most striking thing that you'll notice is the motion of SO2. So SO2 goes on an incredible roller coaster ride. It comes whipping around and then back out.
For an object to have enough gravitational pull to send SO2 on rapid orbit around the center of the galaxy, it must also have a huge mass.
SO2 goes around once every 15 years, and what it tells us is that there is 4 million times the mass of the Sun confined within its orbit.
Astronomers know of only one contender that has a giant mass but is so small.
So that's an incredible amount of mass inside a very small volume, and that's the key to proving a black hole.
And so, at the center of our galaxy lies a massive black hole, an object whose gravity is so strong, not even light can escape it. This is a real image of the center of our galaxy. We can't see the black hole, but we can see bright clouds of dust and gas spiraling toward it. We're nearing the black hole. It's at the center of a stream of dust and gas. The debris of stars blown apart after straying too close.
Black holes grow with time, and that happens by material falling onto it, accreting onto it. And that material can come in the form of either gas or stars that get torn apart by the black hole itself.
At the center is the invisible black hole. This is the material it feeds on. The glowing region is the accretion disk. Here, star debris falls inward and whips around at astonishing speed. Friction heats the debris up to such high temperatures that it glows white hot.
So at the center of our galaxy, we do have a black hole. We now know that today, but it's not producing a tremendous amount of energy. So it's perhaps, we could say, it's a black hole that's on a diet. It simply doesn't have a lot of material to feast on.
But what would happen if SO2 and the other stars were pulled inward by the black hole?
What happens when that material falls onto the black hole is that the black hole, there's radiation associated with the black hole, and it can generate these jets squirting out from the center of the galaxy.
Spewing out subatomic particles close to the speed of light, the beams are like vast cosmic searchlights. This is Messier 87, a large elliptical galaxy that has a supermassive black hole at its heart. It's feasting on its own stars. Shooting out from its bright core are jets that travel over 5,000 light years.
I like to call these the prima donnas of the galaxy world. These are the 10% of galaxies that are show-offs.
Astronomers believe that the massive black hole at the heart of the Milky Way has been there from the very start. But in order to get back to where the galaxy first began, we have to travel out to the oldest neighborhood in our star city. We're traveling upward, away from our solar system, out of the spiral arms of our Milky Way. Up ahead lie vast clusters of stars that orbit the heart of our star city. There are over 150 of them. These satellite towns, called globular clusters, hold the answer to one of the greatest mysteries in astronomy: the true age of our galaxy.
Globular clusters are really fascinating groups of stars. They contain about 1 million stars each. And the thing that's really cool about them is the stars are really tightly packed.
If you could visit a globular cluster, the night sky would be spectacular. Many of the stars would be as bright as the full moon.
And the nighttime sky in all directions would be filled with bright nearby stars. It would be like fireworks all the time.
Besides the sheer number of stars, there's something even more intriguing about these clusters.
One of the very interesting aspects of globular clusters is there's no sign of young stars.
Stars are like people. Look at them and you can guess their age and the lives they've led. with